This is the 260 lecture 5, the principal component regulations. So last week we introduced the random process, and we did some quick review on probability theory, right? So you're supposed to be ready for actually studying common filter in depth. But this week, you are working on the context-oriented project, and you're learning correlation of signals and orthogonality, and that's a very important part that you should experience before going to a common filter. So this week, today and Wednesday, we're going to discuss another very important aspect of statistics and data analysis, right? Specifically, we are interested in large data, and many of you are dealing with the high dimension of the data. I can't say a big data, but I know not only the kind of iPhones and that kind of an IT related the big data, but also in many of the engineering programs. I just chatted with a few people in ocean engineering. They deal with the large area, and actually many measurements are being made. And also folks from Stanford and also Neville Hogan's lab, they all deal with the human movement, which is actually a high dimensional space, and 200 muscles at least are involved in our body, right? So really, we have to deal with the large data. Now these days, it's rather easy to get the measurements. So in a sense, we go to a measurement and look at the data first before designing the systems or synthesizing the control systems. So I would say this would be kind of data-driven system design and a control design, and that it seems to me an emerging trend. So we like to look at some of the basic techniques in dealing with the large data. So yeah, we look at the least squared estimate, and then in that we assume that phi I, phi transpose, yeah, this regressor matrix is assumed to be a non-singular, right? You have to have enough the data to make this space to be matrix to be non-singular. And going to recursive least squares, we assume that the initial P matrix, P naught, must be positive definite, right? And these are, this type of assumption may not be the case if we deal with the extremely high dimensional space. M is a dimension of, the space, and that's actually the dimension of the regressor phi. And M is much larger, okay? Maybe many hundreds and thousands. Now, there are a few cases, where we deal with the high dimensional input space. One is actually a temporal case. So to think about a FIR, finite impulse response model, but you have some slow decaying mode. So as you can see here, yeah, this curve, going down slowly, you have to have many samples over here. So UT minus 1, UT minus 2, many of them are actually have a long list in phi, right? So, yeah, and also, when we look at the, yeah, and sorry, this is the typo. This must be U. I'm sorry, UT minus M. Now, also, when we set the time windows, on the output side, that may be wrong in some situations. We discussed this later in the system identification case, but I know it is clear that the time when we deal with the time sequence, the list of previous data points time windows may be long, right? The other situation is spatial. So dealing with the two-dimensional image or three-dimensional image, in this case, the number of pixels is basically number of row times the number of column. So say even just 100 by 100, 10,000, and so that's a high dimensional. Now, even worse, maybe spatial temporal situations where you have this two-dimensional images, but not just a snapshot image, but you deal with the time sequence image, then actually expanded row times and column times actually time windows. So that's actually a huge dimension. Okay. The other situation is actually limited sample size. So capital N is the number of the data points we take, right? And in some applications, in particular biomedical areas, you can't get the many data points. Some clinical trial data or biological experiments, you can't actually get the many the data needed. And COVID-19 vaccine is being tested. It's basically stage 3, 30,000 subject being tested, right? Each case is very costly. So concerning the complexity of such a system, so human body, right? So many parameters involved. The number of sample size actually is rather limited compared to complexity of the systems. So in many cases, we do see the situation where it is hard to satisfy this non-singularity condition. So you study 3 methods to deal with the you have to n smaller than m, and this guy is not actually non-singular. So if I write and concatenate each data, phi 1 and consists of component 1 to component m, and if I write it in this way, we deal with the situation that the m is basically larger than n. So this kind of rectangular situations. Okay. And the first method is the use of the pseudo inverse, and the second method is the regularizations, and we just focus on ridge regression. And the third case is a statistical multivariate analysis. And then these 2 are major points this week: principal component regressions and partial least squares regressions. Let's start with the first one, pseudo inverse. I don't know how many of you have actually studied the Moore Penrose pseudo inverse, but this is the kind of tools people use quite often in this field: the controls and signal processing and statistics, and so it is worth studying this. So this is actually my quick, just-in-time math. So in conjunction with the linear simultaneous equation, AX equal B, where A is actually an m by n matrix, and B is actually just a parameter vectors, right? Then in a pseudo inverse of A, we denote it A sharp. Many literatures shows sometimes A cross, just the plus sign A cross. Yeah, sounds this technique is really powerful. It's just a god. So maybe they put the A cross. But other literature, they use a sharp. So I know, let me use a sharp, okay, A sharp. So, there are two, cases. This, linear simultaneous equations, AX equal B, can be treated. And then pseudo inverse provides the solution to the following two programs, okay? One is actually the case where no solution exists to this equation. The solution exists when the rank of A equal the rank A concatenated together with the B, right? That's actually things that you learned. Now, if you have more actually, AX equal B can be broken down to many, linear equation. Basically, an X have to satisfy all these constraints, right? So that is determined by actually M. So if you have M, equations to satisfy, but you don't have that actually, many the dimension of X, and is smaller than that. No way to satisfy all the conditions to satisfy involved in this, linear equations, right? So if that's the case, then the pseudo inverse of A is basically to provide the least squares solutions. So making this prediction error, right? AX is something that you can create with the X, but it's not exactly the same as a B. But squared errors is to be minimized. And that is given by this. And this is exactly the equations that we use for least square estimation. So the solution can be given by X hat equal A pseudo times B. Okay, and if you apply this to your problem, you get exactly this equation, which is actually broken down to this guy. You can write it this way. So that's the case when you have too many equations to satisfy. The other situation is that you have many basically infinite number of solutions to satisfy this. If M is smaller than N, you don't have many equations to satisfy at the same time. So you have many solutions to X that satisfy. They all satisfy these equations, right? Pseudo inverse at that time is to pick the particular solution that is actually minimized its own squared norm. So it is to satisfy, it is to minimize this in its own squared norm subject to X equal B. So this pseudo inverse solutions is to provide, it's to satisfy this condition. In addition to that, it is to minimize, this, squared norm conditions. Okay, both, cases can be solved by using the pseudo inverse A sharp. More mathematically, the definition of pseudo inverse is actually given by this. So this is the work done more, in the Penrose, and they did it, independently. So, pseudo inverse is the one that satisfy all these four conditions. And, well, actually A is on the complex, on the number. So when you take the transpose, you not only you take the transpose, but you have to take the complex conjugate of the original complex number. So, we did with mostly real number. So forget about this C, you can replace this star by just a transpose, okay? If A star, A sharp is A inverse, if matrix A is a square matrix, that's actually, and non-singular, these four conditions are obvious, right? So A times A inverse times A equal A, right? A inverse times A and A inverse equal A inverse, right? But if you deal with the situation where A is not the square matrix, and that's not a trivial job, okay? And that's actually given by the pseudo inverse. And A transpose, excuse me, A times A pseudo, if this guy is inverse, so this is just I, so it's actually a symmetric, right? Symmetric, right? In fact, the matrix A that satisfied all of these four conditions is determined uniquely, yeah. By the way, the first two conditions alone, so it's called the generalized inverse, and that's not unique, right? But the four conditions, if we put them together, symmetricity added, it is actually uniquely determined. And then that is to provide these actually properties. So, this is a physical sense, okay? This has stuff, nice properties. And, you can use these four conditions as properties of this pseudo inverse. Okay, now, yeah, so with this, you should be able to show the least square estimate below is given by the pseudo inverse of the matrix, concatenating all the regressor, the vectors. So I already used this notation, phi1 to phi n, or concatenated, creating the m by n big matrix. It's called a regressor, right? So I know this is the solution to the square estimate, right? And we assume this one is to be non-singular. If this is the case, that is actually given by this pseudo, find the pseudo inverse and then take the transpose and then multiply by y. So this can be written this way. And I want you to derive this on your own. One key thing is that the linear equation associated with this this square estimate can be written this way. Yeah, so take the transpose of this data matrix phi. So if you take the first row of this transpose, it is to pick the phi1, right? And then that one is multiplied, take the inner product with theta, and then that is to be, you wish that one to be the same as the first component of output to y, y1, right? And the second equation too, pick up the phi2, inner product with the theta should give the y2. So that's actually the whole equation. So this one is the wishful linear simultaneous equation to satisfy that we want to minimize the error from this point, and that's given by this. Yeah, I want you to derive this. It's just a good practice you should take. Okay, the second method is regularization. Okay, and this is another way of alleviated the difficulty when you don't have much data or input space is too large, so you can't use you can't actually compute the least squares estimate. So what you do is the following. So we consider this type of cost functional. Functional means actually functions of functions. So inside of this, we have many functions involved here. So I would call it functional. And this one is penalty function. So one requirement here is to minimize the squared prediction error, right? So this one is written in a matrix form. So I know we discussed this guy, that this is the wishful, this is something we like to achieve, but I know we have some error, and the error is actually evaluated by taking the, by moving y from the right to left, right? So that's actually the difference, and then that is given by this equation, right? So this is the, squared prediction error. We do have the second term over here. Second term, similar to pseudo inverse, we put the thetas, the norm to be actually, we want to make it smaller. So, among many the thetas, that is to, make this one small, but also we like to pick the one where the theta's norm is to be, smaller, okay? So this second term is to, make our least square estimate, not the ill-posed, well behaving. So, this is another, term, and this is the term to regularize this algorithms. Okay, eta is any, positive number you want to pick. Okay, so, but an interesting point is that we need to find the theta, not only making this one small, but also this must be considered. So we make some kind of a trade-off between these two requirements. So sometimes these two are conflicting to each other, but you have to take into account these. Okay, so find the parameter that minimizes this VR theta with respect to theta, right? So you can actually compute this by by taking the derivatives with respect to theta and set it there, 0. Same thing as before. So this squared the norm can be expanded in this way. Basically, this inner product, and this one too can be written in a product form, right? So we differentiate this. First, we expand this y transpose y, and then this times this, and this times this, and altogether 2 times this. And then this times this, taking the transpose to theta, transpose to phi, and then the phi transpose to theta. So that shows up in here. And then the last term is this. Okay, last term is this. Okay, so let's take the derivatives and set them 0, and you can compute this very easily. I know y doesn't include the theta, so it's 0, and then the theta and the theta, quadratic forms are involved in here. And then what you end up with this guy, matrix phi transpose theta plus eta theta equal phi times output y. Okay, this is what you get. Okay, now factoring out the theta, you get this expression. Okay, so this one is related to the normal equations. In the case that we have no second term, we look at only this term. We don't have this term, so that's like the normal equation. Okay, we discussed it before. Well, looking at this, here's an interesting point. Phi transpose and this guy is questionable in terms of the singularity, right? This can't be a negative, but this one is only positive semi-definite. So you can't invert this matrix. However, look at this. The I is identity matrix, right? Identity matrix with some positive number, eta. And then again, this one has never been a negative. This one is a positive semi-definite. So this as a whole is to be positive definite. Then this particular one is actually invertible. So inverting this, we can get this, solutions. So as long as eta is positive, and we can get the unique solutions, and then there's no singularity problem occurs, right? So beautiful. So regularization is a rather standard technique. When you have some difficulty in handling some singularity and a lack of data, or you pose a problem, but you have some idea what the desirable solutions would be. Well, in this case, we like to make the theta not to be too large, right? Somewhat reasonably reasonable scale. Or if we have some initial guess for theta, maybe theta not, or to something, it should be around this value. If we have some idea about it, you can put it in here to regularize this minimization process. And that's exactly we have seen in the recursive least squares, right? In chapter 2, section 2.24, we did not cover explicitly in class, but we touched on that briefly. We saw that this second terms is involved, And then with that, actually, we understand the process of how recursive least square really works. Anyhow, let's push back to this, okay? So remember recursive least squares, we have to provide the initial conditions, right? By the t equals 0, that's the initial conditions. And then we have to provide some initial guess of theta naught, and actually p naught, then usually it's an identity matrix, something positive definite matrix, thereby it's an invertible matrix must be provided, right? Now let's actually do some thought experiments in the following way. So we provide the theta naught as initial guess, and actually p naught as initial matrix value, right? But before this time t equals 0, we had some class of group of data, phi something y something. Okay, and by putting together this phi and the phi transpose, that is to give the initial p naught that we thought. Okay, and also with y, b naught is also computed. Now, by putting together these two, theta naught is in fact it's given by p naught and b naught. That means that the theta naught is the optimum estimate given that this actually group of data, which we assume phi to be making this matrix to be invertible, non-singular. In fact, given some positive definite matrix p naught, there's some mathematics that we can actually divide this guy into matrix products, vector products like this, a series of vector products, and that is something that we study later on in conjunction with the kernel functions, the data. But for the time being, let's actually assume that there's some actually the data like this that is to provide you with this p naught and theta naught. Okay, theta naught. Then we can actually apply the proof of the recursive least squares, right? Now, with this, and then also we got the new the data comes in. So not only this data, but also this data, and then we can determine the best one that is to minimize the squared error from this data, right? Right. So that is the kind of the techniques that we described in this chapter. But obviously, if actually we consider this kind of penalty, okay, penalty, and we like to find the theta naught, theta that is minimize this, and then your answer on that's t equals 0 is theta equals theta naught, right? So if you pick the right one, this is to be 0, minimized, okay, minimized. So the idea is that let's add this term into this. Okay, so at least if at the time t equals 0, there's no term like this. There's no time like this. If this is the only thing that we need to satisfy, and the solution is trivial, the theta equals theta naught, right? And when we actually receive the first data t equals 1, you add just the first element, the yt minus phi transpose t theta, right? And you have to consider this and then make this other whole to be minimum, right? And the answer is very close to theta naught, right? But however, as you gain more and more data, and actually t equals t, we have say 20, 30 data already here. And that's compared to this guide, this one is actually more dominant part. So the answer minimizing this one is departing from theta naught, going to the more better estimate reflecting the newly obtained data over here. So in a sense, this guy is a regularization technique. At the time t equal 0, we thought we had some idea theta is to be theta naught. Okay, theta equals theta naught. We have that idea. Why not actually putting this one into here, just as we did here, just as we did here. Okay, we did here, right? So putting this one in here, and then now this one theta is replaced by theta minus theta naught, right? And that's actually the initial guess, and that is used here, to regularize this. But the beauty of this method is actually, that we start with this kind of initial conditions. It is guaranteed that every step we get the optimum ones, right? The optimum one. But if you start with the theta naught, which is away from the true theta, then actually it takes some time to catch up with it. The previous data and the new data are very different. Then actually takes some time to get into this part, but that is something we can deal with. Okay, so that's the second method. Maybe I should check the your questions. And do you have stop sharing any? Oh, chat many questions. Okay. I think iPad only for graduate. Okay. Brian, okay. All the students, okay. Question, when would you use ridge regularization instead of recursive square if both can be used with the inline date? Oh, okay. So, yeah, Charles' question, when would you use ridge regularization instead of recursive squares if both can be used with the the data? Yeah, that's good questions. Well, let me just push back to this. Yeah, I just mixed the two stories. So that makes things a little bit confusing. Ridge regularization. This one is not for recursive least squares. This is just least squares estimate. Even though you do not do things in recursively, but if you have some problem with your data, right? You can't get the unique solutions and to satisfy that actually data points, right? So this method can be used for that purpose. So this one is not. This one is for batch processing. It's not actually recursive stuff, right? So yeah, so one question is that then yeah. So when we have to deal with the huge input dimensions and a very limited number of data points, right? You can't use just a standard least square estimate. You end up with the too many solutions, right? Too many solutions. So if you use the pseudo inverse, by the way, if you use the pseudo inverse like this, there is a case, the second case, and it picks up the one which is to minimize its own norm, right? But you can't actually do this computation because this one is actually rank deficit. It's not the invertible. So one is that you can use this pseudo inverse, or it's very similar to that one. You can actually use this ridge regularization. That is to give this solutions. Okay, it's a little bit different math, and there's some the difference between the two, but the concept is very similar in that. Okay, of course, the regularization is very broad, and it can be used for recursive least squares, and then in fact there's certain techniques involved. And we can convert this one to recursive version, And instead of using the some guesswork of the initial conditions, some may use this guy. That's the same thing as you use the theta not equal 0 for your initial conditions. Yeah, there are close relationship among them. Okay, now let's look at the third method. That's a statistical multivariate analysis. Okay, and then let me start with the this here's situations. We like to examine relationships among the multiple variables in a high dimensional space, right? And we like to examine the joint behaviors of multiple variables, x1 alone, and not dealing with x1, x2 independently alone, but we like to examine what happens when x1, x2 jointly behaves. Okay, if we do so in a high dimensional space, we may find some variables are redundant, or if we pick the two variables, they may be linearly correlated. So yeah, what I mean by that is that you have xy axis, right? And then two variables in this axis and this axis, they are basically on the straight line like this. Oops, this is a straight line. So what you see here and what you see here are basically the ratio is fixed. So you don't have to use two variables independently. This variables is basically subsume the role of these variables. That is called collinearity. So in high dimensional space, we often see such actually redundancy or collinearities in the space. So what we like to do is to extract the succinct and significant variables behind that actually in a high dimensional space. And extracting such things is called the latent variable method. This is to find hidden or encapsulated variables in the raw data, and that represent the original data in a low dimensional space. And then the model created through this is called the latent model. Okay, so this latent model is a very important concept. And so here you have a high dimensional input space. But by examining this, you found that the truly independent and meaningful significant variables is not actually M originally, but M star, smaller actually dimensional space can represent the original data equally well. Okay, so if you can actually compress the data in this way, then you can easily predict the y as a functions of input in a low dimensional space. So in fact, if you start with the linear regression, y equals regressor phi transpose theta, this one a low dimension, so you don't have many parameters involved in theta to estimate, right? So that's much easier. If the original one is say 1,000. Theta is to be 1,000, and you need to find the 1,000 parameters to determine this. But if this one is actually reduced to say 20, only 20 parameters involved in the theta is to be determined. So that's much a simpler problem, right? So yeah, let's discuss that. But before doing that, I like to speed up a little bit. Yeah, the one important step that's called pre-processing, and yeah, in a sense, we compare two variables or multiple variables, but they may have the different units and the different actually scale. So, for instance, one regressor, okay, consists of 3 variables, and one variable is basically related to a mass in 10 kilograms. And the second variable is the speed, 5 meters per second. The third one is kind of size in 2 centimeters, right? So if you look at the naively, put into your computer 10, 5, 2, and then do some analysis, the result will be very different if you use just different unit, like this one is 0.02 meter. This number looks very smaller than the previous case, right? So depending on if the units are different, you can't make apple-to-apple comparison. So before going into any analysis like this, we do the following. One is mean centering. We are interested in the variance, So, first you compute each variables in 10 kilograms, but mean value of many, data points that we look at, mean value is 8 kilograms. So if that's the case, we shift the, coordinate origin to that mean. So this turns out to be 2 kilograms if mean is 8 kilograms. So that's the first step. The second step is actually scale. For instance, first variables distribute, from here to here. Second variables is much wider, here, right? And then actually, it's a little misleading. I just put in the same axis, but they could be different in unit, right? So one way of doing this is to take the standard deviations and divide it by that one. Or sometimes people use the max minimum. That's actually the data varies from this minimum value to maximum value. So this is a dynamic range, right? Divided by dynamic range. That's one popular case. That depends on the whole problem. So I don't spend too much time on this, but it's all dependent on the problem. So there's no single reference value to use, but depending on the variables. The program that you can find a good one to do that. But suppose we do this kind of mean centering and then normalizations prior to data processing. So what we like to do is actually this is the first method, principal component regression, a multi-input and a single output case. Okay. So examine how input data are distributed in high dimension, m-dimensional space, and reduce the space to a low-dimensional ones. The distribution can be characterized with the covariance of pre-processed input data. So now instead of using phi, the regressor, I use the mean-centered and normalized regressor, x1 to xm. And put in the same way as before. So now capital X is my data matrix. Okay. Now what we like to do is to check the covariance. Okay. Last week we introduced the covariance of two scalar random variables, x, y, and the definitions of that one is actually use first subtract the mean value from x, and then another variables you take this one mean centered, and expectations of the product of two random variables. That was actually a covariance that we defined in last week. Now here the x and y variables are not the scalar but a vector. Like this case, we have x1, xm, and this one the same process of autocovariance in x1, xm and x1, xm. Well, let's assume we have already mean centered, so we can take the product directly. So if this is a case, this combines, this includes all the combination of these two vector components, right? So first one, x1 square, and the second one, there may be x2 times x1 sitting over here. So you have m by m, combination. So although this one is a symmetry, and you can exchange this, but quite a few components involved. So this is a collective representation of this scalar, covariance. We call this a covariance matrix. Okay. So now, what we'd like to do is actually, using this to do, the data compression, input, order reduction. So first, let's actually see the physical sense of a covariance matrix, and then we use it for latent modeling, right? So I know this is the really recap and examine the strings of signals in the direction of unit vector v. So you see m-dimensional space, and we set the unit vectors, and then we project all the sample points onto the lines of this unit vector, and this is the strength of this signals in this directions, right? And then we take the average of this, and then actually rotate this unit vector in all directions and try to find the largest or smallest the value. It turns out that that is basically we learned this. So projection onto V vector can be represented with this inner product, right? And taking a square, we can expand it this way, right? So this is actually put in back to back this way, and we can factor out the V transpose and the V in this way, right? And if you look at this one, this is nothing but the product of concatenated two matrices x1 to xn, and actually it's transpose. So this guy is actually column vector, and then this one is row vector. Okay, so let's pick the j components over here, and then multiplied by say k components sitting here. Maybe this line is k, right? So if you multiply j components with the k components here, that's actually sitting the jk elements in this matrix, right? So that this one includes all combinations like this. jk is actually from first the samples to the last samples. We can take this. So if we have enough sample points, this one is almost expectation of xj and xk. So by doing this, we can actually approximately compute the covariance and multiplied by sandwiched by a unit vector, and then that's actually give the this quadratic form. And then if you find the strongest directions of signals, you can use the Lagrangian multiplier here, and then differentiate it with respect to v, and then the result is x transpose v equal lambda x. That means actually this v, which is take the either maximum or minimum or extreme values, is basically eigenvector of this matrix xx transpose. And you can put in the from the on the highest one to lowest one, and putting this one, and then actually never being a negative, lowest one, the lowest possible one is 0, right? So back to a principal component to regression. So you have a lambda 1, the largest, to smallest lambda m, right? So now we are considering the case where xx transpose is basically covariance C, and this guy is singular. So if it's singular, this must have 0 eigenvalues, right? So this is smallest one, that should be a 0, right? But maybe second from the last lambda m minus 1, 2 is 0, and some number of eigenvalues must be 0. Right. On the other hand, up to m star, you get the non-zero lambda. So if you represent, this XX transpose matrix into a Eigen decomposition, you concatenate all the Eigen vectors with unit lengths, and then put in this one and the transpose ways. And in the middle, you have eigenvalues, lambda 1 to lambda m, and then the rest of the part is all 0. So if you expand this one, multiply this, you get the lambda 1 times v1 transpose, and the lambda m star, this is the last one, bm star transpose, the rest of the part is 0, This part is 0. That said, actually, we have, if we deal with the high dimensional space and then compute this covariance, we have lots of actually zeros coming out. And we can truncate it at a certain point, even though this lambda, m star is not exactly 0, but in many ways, round of error comes in and not exactly 0, but we can ignore that, truncate it, right? So here's actually a metric people use for truncation. Denominator is all complete lambda 1 to lambda m. Okay, and upstairs is, if you truncate it at the k, we include the lambdas up to that point, Okay, and then we represented the percentage of 100%. So if you include everything, this mu k is to be 100%. So for instance, in the first one, which is biggest, the second biggest, descending order, you write in this way, right? And if you actually add all these, that's actually given by this, it is going up, up, and up. And then finally, it's reaching the 100%. But before going there, we have many, many small, eigenvalues that you can actually, delete, omit. So setting up some threshold to say 98% of the data, belongs to, first m star eigenvalues, and that's actually a good approximation, right? So approximation accuracy can be evaluated by using this percent accuracy, metric. So with this, principal component regression, it can be formulated in this way. So step 1, reduce the input space and represent it with the principal components. We concatenate at certain points, or this one, all very much 0, right? And then we define the m star latent variables using eigenvectors associated with the top m star, most significant, largest eigenvalues. So what you can see here, and actually m-dimensional space. So this is a mean center, the x1, x2, and sorry, this is a typo, xm. Now you compute the eigenvalues and eigenvectors, and so this is the direction of v1 and having the largest eigenvalue, and then this is the smallest one, and beyond that is all 0. Okay, the 0. So what that means is that all data points are confined within this m star dimensional space, right? The hyperplane, I would say. So if you actually have data points x, this should be represented with just in this particular 3-dimensional case, the 2 variables, and this component and this component, right? If m star is just a 2, then 2-dimensional the space. Not the 3-dimensional, 2-dimensional space. So x value can be represented with the 2 coordinates. One is actually take the inner product between this vector and then this x1, the v1, and then or projected onto this line, and then this length is the new coordinates or new variable called the latent variable z1 v1 transpose x. And then projecting onto this Vm star, we get the new variable Zm star equal Vm star transpose X, right? So you have a set of new variables, Z1 to Zm, which is actually lower than the original dimension. And with this, we can construct a low dimensional regression. We regress the data on the Z1 to a Zm star. And then actually, that is much easier program. And then as you can see here, Z1 to a Zm star, excuse me, the lambda 1 to a lambda m star are actually non-zero positive. Therefore, if you put together this matrix with respect to Z, that's actually guaranteed to be non-singular and invertible. So you get the unique solution to these parameter vector B1 to Bm star. So that is the the method being used for principal component regression. Okay, let me just check your questions. Oops. Okay. How good does the initial guess have to be for regularization to be effective? Oh yeah, that's actually Brian, that's actually the last part. So this is actually not the science but the art. So any kind of knowledge, for instance, if this parameters are to be used for representing some dynamical systems. And we know the dynamical systems is to be stable. Okay, parameters, estimated parameters shows unstable ones. That's really a disaster, right? So you have to regularize it. We have to put some kind of stable, say poles, stable, parameter values, to make that happen. So oftentimes we use some very conservative estimate. You really want to avoid a certain bad behavior. Yeah, which is a little bit difficult to do, to representing with just one parameter vectors, and sometimes it's a little challenge. But if you have some knowledge as to how the desired value should be, then you can go for this method. Okay, back to this principal component, regression. We let me just this. So I think the concept is super simple, right? The concept is very, very simple. Because that the principal component, finding the direction where that the signal is the strongest. We gone through it, right? So within this kind of ellipsoid, you can find the direction which is actually the data is actually distributed. You can eliminate the kind of direction where the variables are not existing. So for instance, in perpendicular to this plane, it is actually no data, right? So that is actually eliminated. Also, that's something that the particular combinations of x1 to xm, doesn't produce any meaningful ones, or redundant, or collinear. These are things that can be eliminated through this method. Okay, now. Yeah, I'd like to actually discuss some of the interesting applications.
Hey, also one question.
Sure, go ahead.
So, is there an issue if like XX transpose has degenerate eigenvalues? So if you have a repeated eigenvalue, will you end up with that?
Oh, okay. Yeah, repeated eigenvalue is a good question. You can actually take the, there's some procedures, basically it is not determined uniquely the eigenvalues, right? Eigenvectors, right? Eigenvectors. The outcome does not depend on which particular eigenvectors you pick. You have some freedom. You can pick anything. Yeah, it should not actually depend on that result. Yeah. So this method is rather robust against that kind of situation. Okay. Yep, welcome. And then applications. So yeah, my question to you is, let's see, where is PCR needed, right? Of course, other than the COVID testing. It would happen to be the same name, PCR. But yeah. Yeah. So there are quite a few situation that we deal with the large data, right? Typically, initially we do not know which variables are significant, so we include many possible variables which may be important, so the input space tend to be bigger. Yeah, and what I just sketched over here are a few examples of which are relevant to your interest. So, with students, you deal with the large actually systems, right? Oceans, huge, ocean monitoring. So even just so you take some grid points and dimension, it's going up to, thousands. So that's actually the problem you're dealing with. Right. Also, I see some students from Harvard and also Neville Hogan's lab, and even someone from Professor Sanjay Sama's lab, if I remember correctly. You measure the human body movements, right? And the human body has over 200 muscles. And even single hand, if you pick, that's actually, 19 joints involved, right? So, and putting the IMU and then taking the human movement, you deal with high dimensional space. And the bioinformatics is another huge area. The genome, right? But now, people are also interested in the proteome. So, all the proteins involved in some organisms is being actually identified. So in the case of yeast fungus, 4,399 different type of proteins involved, and that was actually identified in 2006. And shown here is autonomous systems to do some bio experiments. So we deal with the quite on the large high dimensional space. Now, because quite a few students are working on bio mechanics, human body motions and stuff. So I'd like to discuss this. This is not this was context-oriented project topic of last year. Now we have a different topic in this year. So let me use this as an example, okay? So this is to measure the human hand motion, okay? If you count the number of joints you have in a single hand, you can find at least 19 joints, okay? 19 joints, okay? Now the central nervous system is to move, control these 19 joints. It does not actually control individual, muscles individually. Rather, it is to send a command to a group of muscles, and then that signals is to control the combinations of these muscle movement as a group, and it's called a synergy. And so we deal with the 19-dimensional space originally as you measure the joint angles, the postures of all 5 fingers. But in fact, you can actually represent that data in a much lower dimensional space, typically 3 or 4, or 2 sometimes. Now, Santero and his co-workers measured the human hand posture, finger postures of grasping some daily chore items, 100 items, such as the, this one is a door knob, a toothbrush, and picking up eggs, as such. Okay, so many different items are grasped by many human subjects, and then they look at the data. It turns out that, and then they do some mean centering and so forth, and then evaluate the covariance matrix, and then actually look at the principal components. It turns out that the only 2 principal components represent the over 85% of the data. And the first component, which is actually represented by means of eigenvector corresponding to the largest eigenvalue. This is to open and close all 5 fingers in phase. Okay, this is actually just open, close. And the second component is somewhat twisting. Some fingers are actually moving in opposite directions or opposite to phase. Okay, so these two principal components represent the 19-dimensional space very, very accurately. So as you actually see this, hand motion is very complex, but oftentimes, as far as we deal with the daily chore things, only 2 or 3 variables can represent the data. That's good, right? So we did some interesting jobs, and so let me just show you video. This is more entertaining. This video, viewed by almost 400,000 viewers. So that's it's quite.
It is well known that the motion of human fingers is controlled by synergy, which is the idea that groups of muscles are activated together by a single control signal. This coherent activation is much more efficient than controlling redundant muscles individually. Through sequencing and superposition of only a few synergies, we can achieve a variation of complex motions that we perform on a daily basis. We want to extend the synergy-based control to wearable robotic limbs.
Every day we use various tools. Say we use a knife and fork, and then we drive a car. And if you use these tools for a long time, you feel that those tools are just extension of your body. So that's exactly what we would like to do with the robotics. You have extra fingers and extra arms. So, if we can control and communicate them very well, you get to feel that those are just extension of your body.
These are the ISR fingers, which are robotic fingers that mount to your wrist. It has 6 degrees of freedom, 3 degrees of freedom in each finger. The fingers are quite long, so the user can grab things that are usually much larger or much heavier than they can do with a single hand. We take input from a sensor glove, which you see over here, and we have these bending sensors that can measure the position of the human fingers. And through an algorithm, we can control the output, which are the positions of the SR fingers, with the position of the human fingers. So the motion can be very natural and implicit. With the assistance of the SR fingers, the user can grasp objects that are usually too difficult for them to do with a single hand. For example, objects that are too large, too heavy, or the surface of the objects are too hot or too cold. You can also perform tasks that usually require 2 hands with a single hand, for example, taking the cap of a bottle or opening a letter. For elderly or people with disability, these fingers can help them to enjoy a living much more independently.
I think.
So that's good enough. And so, yeah, that's a quick introduction. So let me put back. So, 19 joints, but we can basically reduce the number of, input space, right? So here's the, experiment. So we had the 2 extra fingers. So we ask, human subject grasp a various object like this, and kind of awkward object in shape. And then we ask them where to put these 2 fingers. And so we ask them to move this, manually. And then we took a lot of data. Okay. So, with that actually, extended hand with the 7 fingers, are there any actually, synergy exist? And so here we have 19 joints for measuring the, natural finger postures. Also, each robotic finger has 3 degrees of freedom, so 6 joints are added. So input space originally 25-dimensional space. And then we put this one. Well, actually, this is a little different than notations. And the X matrix, this is one particular measurement. And we have totally 40 measurements. And then individual measurement is basically, taking the humans 19 joints measurements, and robot the 6 joint angles are all packed and place this in row vector, not column vectors. And actually, that is actually the conventions in the data analysis field. But I know this course includes the systems of dynamics and control, and then control field, and all the vectors are basically column vectors. So it's a little different. But anyway, so be careful about that. But other than that, the same. So we first mean centered and actually take the covariance of this, and we did the principal component analysis. So input space is 25 dimensional. So we have 25 eigenvalues. However, many of them are just 0. And the first principal component is actually the largest. So this one is explained 65%, and the next one is about 18%. The third one is like this. So principal component, eigenvalues going down, down, down like this, right? And then almost 5 or 6, it's almost reaching 100%. Yeah. So this is that actually percent accuracy curve. We go this way. So we can truncate it, well truncate it at the 3 in particular, then actually 95% of data can be explained. Now, what we would like to do is not just finding the synergy among the 7 fingers, but we like to control these 2 fingers, right? So we apply the principal component regulations. So based on 5 fingers data, we like to predict these 2 robotic fingers postures. And if this is the case, how we really do that. So in here, we use a lot of different data matrix. So input space and output space are separated. So input space is 19-dimensional space. So this is the input data matrix, and the output is 6-dimensional space. So we split these 2, and then we find the relationship between the 2, but we do not go directly to deal with the 19-dimensional space. Instead, we basically reduce the dimension by using the principal component analysis, and then reduce the space to say 3 principal components. And for that 3 components, this output is actually regressed. So this is first the components. So first one is to open this finger to 5 fingers in phase, and open and close. And then actually all in phase motion. This is the second mode, which is a little different. And the third one is somewhat twisting, out of phase motions is involved. These are basically obtained by analyzing the principal components. So now we know 3 components will be good enough, all right? So instead of dealing with the 19-dimensional space, it's harder to measure this for practical applications. Instead, through this preliminary analysis, we found that the 3 latent variables, or reduced the space, 3-dimensional space, is good enough, right? So, based on these 3 variables, we can actually, correlate, 2 fingers motion, which is actually 6-dimensional motions. We actually regress on these 3 variables, Z1, 2, 3. That's the way we did. Yeah. So that's the story for today. What time is it? Oh, we still have some time. Okay. So I guess I have, demonstrated in some way how we deal with the high dimensional space, right? And don't go directly to create the regressor from the original high dimensional input space, but examine what's in there, and then open we find the latent variables, Z1, Z2, Zn star, that is to well represent the input space. So we regress on these latent variables and Z1 and Zn. Now I see a few questions. Okay. How many separate data points needed to be? Yeah. Yeah. Anubhav, it's a good question. We took, in fact, we took more than 19. Yeah, we took 40 data points, right? We asked human subject to take many postures, 40 data points. Of course, the end result will be a little different depending on how many data sample points you use. Then that's actually not the clear point. But what we did was we first started with the smaller samples and actually increased number of samples. And from certain point, no matter how many new data you add, the result doesn't change very much. So that's a point that I got that may be good enough to address those things. So in fact, m equal n, capital N is larger than m, but in fact, the input space can be reduced to a very low dimensional space. And in particular, human motions, right? We have high degrees of freedom if you measure the all motions. So if you put the IMU to each of the part of the body, right, you can move up to a high dimensional space, right? But in many ways, the human motions are correlated in some way. And some variables and other variables, they move together in certain directions with this certain ratios. Then actually you don't have to use the two variables, right? You can actually put them together, reduce that, and replace it by just one variable. And this principal component analysis does this in a very systematic way. And then at the end, you get the smaller number of variables that is actually much easier to use for estimating the predictions. Yeah. Okay. How do you deal with the task that requires the human fingers and the robotic fingers that don't follow the same synergy or anti-correlated? Yeah, sorry, I know. The last part, okay, how do you deal with the task that requires the human fingers and the robotic fingers don't follow the same synergy? Okay, but maybe for first starting with this. So, of course, the offline data collection, data collected in offline, right? That shows a certain actually behaviors, and then we found that can be reduced to a low dimensional space. Yeah. So yeah, and then when a robot tried to do something, a human tried to grasp something, novel object, novel case, there's no corresponding the data point in the past. However, this method is in a sense interpolate the closest data point. We somehow smooth out the curve and then input out the relationship is to be interpolated based on the on the data provided. And interestingly, at the end we measure only 3 variables, right? Yeah, so in both yeah. So at the end, we use a. Can you see it? Maybe. Let me do it once again. Boom. Boom. Well, in this case, at the end of the day, we use only 3 sensors attached to the human fingers, right? So if it is to grasp some novel object, we detect only 3 variables, Z1, Z2, Z3, the latent variables are associated with the 3 significant eigenvectors, right? So yeah, Z1, Z2, Z3 are actually determined. However, each case is basically take the value in the three-dimensional space, Z1, Z2, Z3. And for that, we actually estimate the desirable, finger positions. So even though the new data, the new object has never been grasped, but it is characterized with this three, variables, and by the linear combination of each of Z1, Z2, Z3 components is to provide the estimate for this. So it is, in a sense, it's interpolated, among these. Of course, the offline data and the new object is totally different. That's a different story. So, offline data must actually, include the most of the object or representative set of object must be taken. That's always the case. If you take this kind of approach, first you take the data, and then based on the data, you configure your control systems or design the sensor systems and such. This is one of the so-called data-driven design or data-driven controls. Instead of just going to design these sensors and systems directly, you first take the data, right? Of course, that data must be representing the task you want to do. So that's actually a key assumptions. But based on the data, you can configure, you can get the guidelines as to how the system should be constructed. Yeah, that's actually interesting part in using the a large amount of data, right? Oh yeah. So how are the bridge? How are the latent variables are measured to estimate the hand posture? Yeah, in the last part I did not explain the details. At the end of the day, we want to use only three sensors, right? So that's actually a type of stretch sensor. That is to measure combination of two fingers and these two fingers, these two joint of the fingers. So that is three measurement with the three stretch sensors, and actually Z1, Z2, Z3 that actually identified from the data must be matched. So we have to do extra calibration to match between these two. Yeah, 3 by 3, 3 to 3, and the matching must be done. Yeah. Okay. Any other questions? Let me see. Any other questions?
Professor, I just have a general question.
Sure.
For the context-oriented problems, is it required that we use MATLAB only, or can we use, say, Python or some other programming language?
Whatever,
okay.
Your favorite ones, right?
Okay.
Right.
Okay.
So for that one, as I said, even though Python programs are already existing, because of these guys are everywhere, so existing. But I hope you code it.
Yeah.
If you are good at another language, that's fine. Yeah.
Okay. Thank you.
Yeah. Okay. So this Wednesday we're gonna actually look at the a bit more sophisticated method. It's called the partial least square regressions, and that is to use something very interesting mathematics, it solved some of the weakness of this PCR, right? So we'll look into that. So this week is really, looking at this kind of large data and how you deal with the prediction. That can be used not only for control design, but also, broader sense of system level design. And starting with the data is very interesting direction to go. Okay. Yeah. With that, have a good day. Thank you. Bye.
Thank you.